Ladies and gentlemen, thank you very much for joining today's conversation. Talk about reliability growth. Now, reliability growth is a term that is used by a lot of different organizations, a lot of different people. And sometimes it feels like we're talking in very different, talking about reliability growth as if it's very different things depending on who you talk to and what background they have. Now, sorry about that. So what I'm going to talk about today is what reliability growth actually is, depending on different perspectives. We're not going to have a single equation. That's not useful, because if we have an equation, then we need to give it context and practice how to use this equation. And that's beyond the scope of today's conversation. But the idea behind reliability growth sounds very noble. We want to grow reliability. So I just want to see if you could show through a show of hands, through emojis or what have you, who has heard of reliability growth and has some preconceived idea about what reliability growth actually is. Fantastic. So a few of us have. Of those people, thank you, Kevin, Jason, Brian, I can see your comments in the chat window as well. Who has done reliability growth in a military context where you're part of a defense contractor team or you're part of the military project management team where you have to come up with a reliability growth plan? Not so many people. Okay. The thing about reliability growth is that there are many challenges to it. And we often like, as engineers, as technically minded people, coming up with ideas or coming up with models or frameworks which break down complex scenarios into things that we can more easily handle. So I'm going to start, perhaps surprisingly, the picture of Trollstigen Road in Norway. Now, as you can see, we're looking down into a valley. And you can see that this is a road which doubles back on itself, has a lot of hairpin turns, depending on which country you're from, or a lot of switchbacks, because there is a huge gradient, or at least significant gradient, for our vehicles and humans to travel. And because of that, we need to come up with a pretty smart way of getting from where we are to where we want to be. So reliability growth is like being on Trollstigen Road in Norway. We're trying to get from this starting point, which is at the bottom, a point of low reliability, so to speak, up to, for example, this point here. But of course, whenever we're designing something from scratch for the first time, the problem with this lovely little analogy is that we don't know we don't know what the path needs to be. In fact, there is no path, there is no road. We, during our design process, during our design production process, are going to trailblaze a path from where we are to where we need to be. And of course, we might have some idea about the challenges we're going to experience, but in reality, we don't know how steep the mountains are around us. And what that means is that when we start our design process, we do not know with absolute certainty what the challenges are going to be, what the issues that new technology bring into our calculus. And in fact, many times we actually don't know where we're starting. So if we think that our product has a reliability of 90% at the start of our design process based on our current design configuration, that is essentially a guess. So it's often a challenge for us to really understand how we need to chart our way from point A to point B, especially when we're not really sure where point A is. And in some cases, we don't even know exactly where point B is, because that is a subjective assessment about how reliable we need something to be. Now, I know I'm not really selling reliability growth a lot, because Reliability growth is fantastic. Reliability growth is where we do things, we change our design, we change our manufacturing process, we change our maintenance philosophy in order to grow reliability. But growing reliability essentially means we do things like design for reliability. And the idea is that there is going to be ideally some optimum path where the combination of what your road building equipment, so to speak, can do, what the environment allows you to do, the distances you need to travel, the ability of your vehicles to go up certain gradients, essentially what the strengths and weaknesses of your design team are, is going to be an optimal route. And of course, this route here is the optimal route, which surveyors came up with a long time ago as the ideal way to get from the bottom of the valley to the top. So design for reliability is all about finding the most efficient path to reliability as quickly as possible. So this is what our DFR curve is going to look like. However, if you don't have a really good design for reliability strategy, then you just confuse effort with outcomes. And this is what effort looks like. We start wandering around. Sometimes we go up a hill, sometimes we go down a hill. But every step of the way, we are working very, 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 very hard. Perhaps we can convey to our managers, look at all this wonderful testing we're doing. Look at these wonderful journals I review. Look at this wonderful literature review. All this seemingly apparent effort. But if it's not controlled, especially focusing on the vital few weak points, we're going to end up over here, which is a point where we actually don't know much about. This is what effort without outcomes looks like. So when we're going to when we're going to start with our process, our design process, our production process, it's all about design for reliability, the most efficient approach to making reliability into our products. The term I like using a lot is the vital few weak points of your system need to be the focus of your effort, not what a standard says you should be doing, not what worked last year. It's all about finding the vital few challenges for your design scenario and addressing them and nothing else. That's what efficiency looks like. Now, a lot of the time we hear about reliability growth in the context of testing. And without knowing what people are expecting from this webinar in terms of the breakdown, I do need to talk about reliability growth testing. It's a good section of a good portion of many textbooks deal with reliability growth testing. There's military standards and military guidebooks on reliability growth testing, and it's a very specific form of testing. But I know Fred's going to enjoy the next main point I'm going to convey first before we start talking about testing in greater detail, where we should always be testing to learn and not testing to pass. This is a very important aspect of reliability engineering. So let's look at some of the tried and true conversations I've shared with some of you in the past who've turned up to my webinars, and we'll start with looking at an engine. And this simply represents the product, the system, the device that you and your organizations are designing as we speak. This engine simply represents the outcome of your production process. And as we know, every system, every device, every product will fail at some point. And let's just say that this horizontal arrow represents the time to failure of your product, your device, your machine. And now we're going to represent the failure of this thing with this blue dot moving from left to right. And unfortunately, our engine failed right at this particular point. And essentially what we're doing is visually representing the time within which our engine was still working. And this blue dot represents the event where our engine ceased working and started to exist in what we call a failed state. Now, we're not going to go into statistics into too great a detail, but we do need to touch on statistics to really understand what it means when it comes to reliability testing. Problem with reliability and a lot of other stuff that just drives people insane is that seemingly identical engines will fail at different times. Now, we all know that the engines, like two identical engines produced in the same production line from the same facility on the same day, we know that there are microscopic differences. We know there are slight differences in terms of where the gasket on one engine sits compared to where the gasket on another engine sits. We know there's differences in where the defects are distributed across the manifold, for example. But for all intents and purposes, if we can't see a difference between two engines sitting next to each other, from our human perspective, they're identical. But we know that those little differences do exist, not to mention the differences that how they're going to be used. And that means that they're going to fail frustratingly at different times and in different ways. So here's my good old random hand of failure, which incorporates material imperfections, variation in manufacturing, seasonal weather changes, variation in how people use our thing, and of course, plenty of other microscopic little details and changes and deviations, which means that no two engines will fail at exactly the same point. And from this hand, we're going to have our data points drop down, and you can see that each one of these blue dots or balls represents the time to failure of a hypothetical engine. And if we had a lot of testing, in fact, this is what 100,000 data points looks like, we can get a histogram which looks something like this. It has a very clear shape emerging, but it takes a lot of data to get there. So that's a problem. Even though we have 100,000 data points, it still isn't smooth, but we do see that a shape is emerging. If we were to hypothetically continue our testing until we had an infinite number of data points, which is obviously not possible, we would get this orange curve here. This is the PDF curve we'd get if we have a million, billion, trillion data points, an inconceivably large number of data points. This represents total knowledge. And now we have a way of characterizing the uncertainty in when our engines fail. Just because something is random doesn't mean it's not predictable. And of course, we want to do things, if possible, to reduce the variation, reduce the uncertainties. But especially when our products are going to be used by consumers who have very different ideas on how that smartphone or that tablet or that engine or that vehicle should be used, it's just in many cases not possible to remove, sorry, I should say it's in every case, it's just not possible to remove all the variation and the uncertainty we would like. And so we do need to use things like the PDF curve to characterize that uncertainty. So that's what total knowledge looks like. And we know that because we see a bell curve for our time to failure PDF, we know that our engine is wearing out. So that's just a characteristic of a probability density function, which looks like it's got a bell shape, it's got a mountain shape, it's got some sort of peak. And we can use this PDF curve to work out that we expect 10% of our engines to fail at that particular point in time. That is indicated by that shaded red area to the bottom left of our PDF curve. This horizontal arrow in the bottom left-hand corner of your screen represents when reliability is going to be 90% or 0.9. So this is just a little summary of all the wonderful information that we have in this smooth probability density curve that a lot of reliability engineering is focuses on trying to understand, or at least better depict. But we can never get to this PDF curve, not even with 100,000 data points. This is it's almost a pie in the sky journey where we try to create this, or try to look for this hypothetical, this mythical PDF curve, which definitely does exist. It's just that our product, systems, or services aren't going to easily share that information with us. We have to try and guess what it is based on observed data. So let's go back to the real world and get rid of the most of our data points and start and go back to a point in time where we have 30 data points. Now, this is potentially a lot of data points for many reliability engineering scenarios. 30 data points, or 30 being able to test 30 different systems until failure is a number of data points that many reliability engineers can only dream of. It's not always the case, and plenty of industries, there is lots of failure data. But if you work in an industry where you are required to produce something that's supposed to be very reliable, it means it takes a long time to have a prototype test until it fails. And so 30 data points in some scenarios might be a lot of information or a lot of data. But you can see that if we have 30 data points, that histogram, which used to be relatively smooth and have a clear shape, doesn't have that shape anymore. So when we do data analysis, we always need to describe our outputs in terms of confidence. And if we have a look at these 30 data points here, we might do some statistical analysis and say, you know what, the most likely, or perhaps the dominant PDF curve that best fits this data, that's a term we like using a lot. The PDF curve that best fits this data is represented with this blue line here. You can see I haven't colored it orange for a very specific reason. The reason why is because we should never focus on just the best guess of our PDF curve, or the best guess of our reliability, or the best guess of the mean time to failure, the best guess of whatever statistic we're trying to understand. We always need to have confidence in our probability density curve. And so what I've superimposed on our best guess for our PDF curve, that blue line, is actually the confidence regions where the outermost blue shape represents a 90% confidence interval. The next one in is 80%, all the way down to 10. And you can see that this now represents the fact that even though we might have a best guess at that underlying PDF curve we're trying to understand, in practice, we need to have superimpose, or at least represent, our confidence in our conclusions, because the data points don't give us all that wonderful information we need. So if we were hypothetically interested in understanding when we expect 10% of our systems to fail, that is going to be a little bit more challenging given this continuum of potential PDF curves. And of course, one way of dealing with this is to get more data. And here's 1,000 more data points. You can see how it reduces the uncertainty, the lack of confidence in our confidence intervals as we go. This is a real statistical analysis, by the way, so nothing is being made up. This is what the updated PDF curve with our confidence intervals on it will look like once those 1,000 data points are added. But as you will probably appreciate, testing 1,000 things to failure in a developmental process is not feasible in many scenarios. But if we were able to get this information, we would be now a lot more confident in predicting when 10% of our systems will fail, if that's important to us. So before we do any sort of testing, including reliability growth testing, we need to understand our decision. And understanding our decision is the first step in coming up with a reliability test. And I like describing reliability testing as an activity which exists on this continuum here. On the left-hand side, we are improving reliability. On the right-hand side, we are measuring reliability. And beyond the right-hand side, sorry, that was me taking a drink, is this other sort of testing we call demonstration. We'll come back to that sort of testing later on. So improving, tests that are focused on improving reliability are those tests where we're trying to find as many weak points or failure mechanisms as possible. Those things we call the vital few. Now, the vital few are the things that, if we were to address, would have the biggest effect on growing reliability. So remember, this is all about reliability growth. The reliability of your system is defined by the usually very small number of weak points of your system's design. And so you don't want to improve anything that's already not the weak point. We want to only improve the relatively small number of design weak points. And the earlier we do that, the less expensive that becomes. But when it comes to measuring reliability, where we focus on quantifying the frequency of these dominant failure mechanisms, we still are driven by the vital few. The vital few drive the overarching reliability characteristics of any system. Now, the thing about tests that improve reliability is they don't take very long and they're relatively inexpensive. But when we need to measure reliability, they take a lot longer and are a lot more expensive. And so that's one of the challenges that us engineers, especially us process-driven engineers, and we all have a bit of process in us, we just sometimes need to know, for whatever reason, what the reliability of our product, process, or system is, product, system, or service is, I should say. Problem with that is that sucks money and time away from improving reliability. So improving reliability essentially is another term for reliability growth. Activities we do that make the reliability of our product, system, or service higher tomorrow than it is today. So measuring reliability can be important, but not as important as making or improving reliability. So reliability growth at its heart looks like this. We have, here's my smart lock. This is an exemplar system or exemplar product I use in a lot of my conversations. So this smart lock is made up of a bunch of different components, wonderful components that represent new and emerging technologies coming together to create a wonderful smart device. To have the traditional mechanical lock technology coupled with smart technology provided by PCBs and all sorts of other things that allow us to, for example, automatically have our door automatically unlock when it detects that our smartphone is about 3 meters away because we're carrying heavy shopping bags from the grocery store. And that's just one less thing we need to worry about, trying to put the groceries down, get the keys out, unlock our front door. If our door is already unlocked for us as we start approaching it, that's a wonderful, wonderful feature. We can also assign temporary pins to families and family members and friends and cleaning people to allow them temporary access to our house without having to let them in. So smart locks are a wonderful example of this new smart technology, which couples existing technology from mechanical locks, combines it with what is becoming more and more prevalent in everybody's house and workplace. But the thing about this smart lock is that what you see on the screen is no more than an initial system configuration. If we were to create a startup company which is going to design the next great smart lock that's going to disrupt the market, we can come up with a pretty diagram like this, and we know there's going to be an electric motor in the middle, and there's going to be a keypad on the right, and it has 2 handles and shafts and clutches and everything else. But this is not a design. This is a basic configuration. A lot of people can get intimidated by reliability at this point. How can we know how to make it reliable if we haven't even designed it yet? And that's where good reliability engineering is all about convincing organizations that we have a wealth of corporate knowledge in our heads already. And before we even start designing our thing, we should already be able to predict what the weak points are going to be. Not going to be necessarily, but are likely going to be. Let's call it that. And so let's just say we conduct a system for MIA or a fault tree analysis or fishbone diagram where we work out what parts of this smart lock are going to be the parts that are going to keep us up at night in terms of the production process. And these red circles represent areas of concern. With the bigger the circle, the bigger the concern. Now, the bigger circle in the middle is actually centered around the solder joints that join our smart lock motor to our PCB. Solder joints are historically weak, especially if this smart lock's going to be in a door that gets slammed a lot. And that's one of the things we can often forget. We design for the perfect customer and not the customer who's going to purchase our smart lock. So we need to be aware that one of the biggest problems our smart lock might endure is based on this configuration, those solder joints fracturing when those internal wires get thrown about inside the smart lock when the door gets slammed. And there are lots of really simple design solutions to overcome that weak point. So when we design that out of our system, we all of a sudden start improving reliability through Vermeers and Holtz and all sorts of different, wonderful, different activities where we keep focusing on the vital few. And every green tick or check mark here represents where we have resolved an issue, the next weak point in the design of our system before we even start doing any sort of detailed design. And so our design team is able to go away and generate this wonderful confidence that comes from understanding and not statistics, that this smart lock is now going to be very reliable. And of course, we now know what the remaining vital few weak points are. So these are the vital few weak points that we're going to focus on when it comes to measuring reliability. So this is reliability growth, where we incorporate what we call corrective actions to remove weak points or root causes or anything from our system that's going to cause it to fail earlier than we would like. So Vermeers aren't technically testing. Holt's highly accelerated live testing is a form of testing where we essentially try and push early prototypes towards their operating limits and then beyond to make sure essentially that we break them. So we identify these weak points. All we're doing here is trying to understand the vital few, get those weak points. But of course, if there is existing data, we should always try that first. And you can see on the screen now, I've just included a small smattering of different sources of data that if you have available, these should help you work out where your systems fail more often than not. So these are the sorts of things we are looking at when it comes to improving reliability. What are the weakest points of our system so we can then incorporate corrective actions to improve reliability? Then we have things like simulation, where we might have, generate a basic understanding of our design. We do things like finite element analysis or finite element modeling to work out where the highest regions of highest stress are, so we can then study that further. But once we've done that, we should have a really good understanding of that vital few, which is there to primarily improve our design, but also allows us to do things like accelerated live testing, where we can focus on those vital few weak points, work out what makes them tick, and create test regimes where we can, for example, increase the temperature or increase the stresses to take 10 years worth of life and compress it down into 10 days so we can get a really good idea of when our thing's going to fail using accelerated live tests. So tests that improve reliability by finding the vital few also help you quickly focus on your measuring tests. But there's also lots of other tests, including reliability growth testing, which we'll come to very shortly. So we have designs of experiments which are often used in manufacturing to help us work out what is going on when we do not understand why some products seem to be defect-free and others don't. For me, is a really wonderful at helping come up with screening tests. Those are tests that essentially identify defective components and take them off the production line. That said, if that's something you need to do, then you're not looking at a very capable or high quality production process. Burn-in testing, we know that if we do some burn-in testing for electronic assemblies, we can remove a lot of manufacturing defects. There's stress margin testing, where we see this classic stress strength interference scenario, and all these wonderful tests, which if you want to learn more about, feel free to email me after this webinar and I can point you in the right direction. But I'm not going to talk about these in too great a detail because this webinar is all about reliability growth. Now, reliability growth and reliability growth testing can be two very different things. We're now going to start moving to the right-hand side of our measure reliability continuum, and we're going to look at tests and activities which essentially deal with, let's call it production-ready product systems or services. So software testing involves taking software code, for example, and trying to see when it doesn't work. And that means we can go back and try and work out what the bug was, what the issue was, and design that thing out of our system. Then there is reliability growth testing, which is build, test, fix. Reliability growth testing is often seen as a test described by this thing called Mill Handbook 189 Charlie, which is seen as the overarching guiding document on reliability growth testing. And it comes down to build, test, fix. And there's a few things that make reliability growth testing appealing to many organizations. A lot of organizations are just enamored by build, test, fix, or sometimes called test, analyze, and fix, as described in that military handbook. Now, there's a few constraints with the build, test, fix, and test, analyze, and fix approach, as described in this Mill Handbook 189 Charlie. And that is, as opposed to building a prototype and just testing it to see where it fails, when you do reliability growth testing, that is not allowed. Now, you might say, well, surely any activity which grows, which will have as an outcome growing reliability, that is a reliability growth test. Well, I concur with people who feel that way. But in practice, the term reliability growth testing is reserved for a very, very specific type of testing, which is not as wonderful as the name might suggest. Because first and foremost, reliability growth testing means we test our product, system, or service in actual use conditions. And that means we can't accelerate the test by increasing the stresses or making things go faster. And if you have a really reliable system, then your actual use conditions mean that you have a long and slow test regime, because you need to get enough failures, observe enough failures to be able to make whatever conclusion you want to make. Another issue with Mill Handbook 189 Charlie is that we have to test the entire system. And that is a real problem, because we cannot test the entire system in actual use conditions early in our production process. So reliability growth testing is often only feasible towards the end of our production process. And what is the problem with that when it comes to corrective actions? I'm going to ask you guys, what's a problem for a reliability growth testing regime, which is built on corrective actions that improve reliability, if the only time we can do this reliability growth test is towards the end of our production process, where we have essentially a borderline production ready prototype ready to go? What are some of the problems that you might think? Brian, usually very hard to make changes at the end of the program. That's fantastic. That is the biggest challenge with reliability growth testing. Sebastian, a change at this point costs much more. Kevin, you will never launch. Those are, and sorry, I see that Adiola says designs have been finalized. You are all commenting on the same issue that it is generated by reliability growth testing. It is actual use conditions, test the entire system, which means we're not just focusing on the vital few, we're also doing the trivial thousands. And it requires essentially a working prototype, which means that this needs to happen after the bulk of your design activity has been done. And it's very expensive to incorporate these corrective actions, to the extent that some of them don't get incorporated. Now, reliability growth testing is based on a phenomenon that was observed by this guy called Dwayne. He worked in General Electric, and he was in charge of testing prototypes to observe their cumulative failure rate over time. The idea of that is that if we had some sort of prototype build, test, fix approach to making a wonderful new prototype of a device, Dwayne, amongst a bunch of other people, would essentially get the prototype from March, put it under test, work out how many failures it had, estimated the failure rate or the MTBF, plot it on a set of axes, send his report back to the design team. They'd go away, design a new prototype, get the new prototype, and Dwayne would then measure the improvement in reliability, et cetera, et cetera. And he noticed that if he was to plot the improvement in reliability, which in this case is represented by a decrease in failure rate, he could generate a straight line if he plotted that cumulative failure rate on a logarithmic scale and the cumulative test duration on a logarithmic scale. And so this downward trend here means that our prototypes are becoming more and more reliable. And in fact, he was able to work out what the slope of this line of best fit was. And this became known as the reliability growth constant, or the reliability growth rate, which is represented by the Greek letter alpha. And so this blue line represents what Dwayne found for typical hydromechanical systems. He then compared what he found for hydromechanical systems with jet engines and aircraft and generators and other devices, which were essentially devices that didn't fit in the first three categories, or the first four, I should say. And he essentially found this very similar patterns, that if he was to plot the rate at which reliability improved, or the failure rate decreased over time, over test duration, I should say, you usually get a straight line in the log-log scale. Now, I'm going to go a little bit nerdy on you guys here, because some of you might have heard of this thing called the Weibull distribution. And it just so happens the Weibull distribution is a distribution whose hazard rate or failure rate appears or manifests itself as a straight line in log-log scales like this. And so we sometimes call this sort of failure rate, where we see a straight line in log-log scale, failure rate with Weibull intensity. Why is that potentially important to note? Well, it's just that the Weibull distribution is what we call one of what we call an extreme value distribution. So it's really good at working out or modeling systems where the system fails when the weakest point of the system fails. And in some cases, it's also really good at modeling systems where the system fails once the last remaining link in the chain fails. But when it comes to decreasing hazard rates, we always, and I mean always, see decreasing hazard rates, whether it's due to maintenance-induced failures or manufacturing defects or improvements over time from the design team. We always see a straight line, the failure rate represented with the straight line in a log-log scale, or a hazard rate with Weibull intensity. And it makes statistical sense. Now, problem with this, though, is as we start getting more and more reliable, look what's happening to our cumulative test duration down here, where the first cycle on our chart went from 1,000 to 10,000 hours. Now, if we want to get a similar improvement once we've completed 1 million hours, then we need to do 10 million test hours thereafter. Brian has asked, isn't this the basis of pro-AMSA projections? And the answer is yes. Brian is talking about this approach to reliability growth which is called the Crow-AMSA model. And a lot of models, when it comes to reliability growth, are based on this underlying pattern you can see on the screen now, which is called the Dwayne failure pattern. And there's reliability growth models called Dwayne models and Crow-AMSA projections and things like that. And there's slight variations on the underlying theme that the cumulative failure rate of prototypes being tested will decrease in a way that creates a straight line on the log-log scale. So the answer to that question, Brian, is yes. So as a rule, when it comes to reliability growth, where we're testing prototypes in at-use conditions, and those prototypes are largely production ready, if you want to decrease the average hazard rate by around 20 to 30%, you need to double the total amount of testing you've done. So there is a price you pay as you become more and more reliable, which makes sense, hopefully, because as your device becomes more and more reliable, you now need to conduct more and more testing to uncover more failures to work out what is wrong with your system. So one of the key points of reliability growth testing is that the only way we learn is through observing failures in this at-use conditions. Now, Brian has helpfully introduced the term Crow-AMSA into this chat window for this webinar, and Crow-AMSA is one example of a reliability growth modeling approach. There's lots of them out there, and I'm not going to refer to many of them by name. That's not the point of this conversation. The point is to try and articulate what reliability growth testing is. And reliability growth testing, in accordance with 189 Charlie, is a very formulaic approach where we need to make a ton of assumptions about how our thing is going to, how reliability is going to grow. And when we do that, we come up with a thing called a reliability growth plan. Now, here's a reliability growth plan that I put together for a military customer. This military customer was in the process of building a military vehicle. Now, this is maybe a confusing chart. Well, let's break it down. On the horizontal axis, you can see that we have test duration expressed on a linear scale from 0 to 200,000, in this case, kilometers. On the vertical axis, you can see we have the MTBF, which is, as we all know, Fred's all-time favorite reliability metric. But it does represent a decrease in the prevalence of failures. It's a very basic measurement of reliability. But as Fred's hysterical response in the chat window suggests, it is technically not a reliability metric. It's all about the frequency of failure, and reliability is so much more than that. It's a factor which drives reliability estimates. But nonetheless, in this context, the MTBF is useful for describing how the frequency of failures are decreasing as we do more testing, uncover more failures, and learn how to design the root causes of those failures out of our system. And so this red line here is the what we call the idealized growth curve. Does anyone know where we get this red curve from? Does anyone know? Yes, Fred's not entirely wrong. Part of it's made up, but we just talked about a particular model. Karen suggests estimates. Yes, you are right, Karen. And Brian's asked, is it based on Dwayne or Dwayne's curves or Dwayne's failure model? And the answer is yes. This is what the increase in MTBF looks like when we take it from the log space that we saw in the previous chart and plot it on the more familiar uniform space. And you can see that the reliability or the MTBF grows more quickly at the start, then it starts to slow down as time goes on. So that's what we call the idealized growth curve. Then we have these black lines here. Excuse me. And these black lines here is for a very complex production schedule. These black lines represent the reliability of individual prototypes. So the idea is when you manufacture a prototype and test it, its reliability is not going to magically improve. So the idea is you work out what its design freeze date was, where that design freeze date aligns with or corresponds with the idealized growth curve, and that is the predicted reliability or predicted MTBF, I should say, of that prototype as we go through this production process. And so these black lines here are what we call the planned growth curves for reliability growth testing. So what's happening for these prototypes? Well, they're being tested, and every time they're tested and a failure occurs, you conduct the root cause analysis, come up with corrective actions, and feed that back to the design team, who then incorporate those design changes into the next prototype's design. And that improvement of design is represented by this red line, which increases the idealized growth curve. And every successive prototype theoretically should be more reliable because it incorporates more corrective actions from the failures observed in previous prototypes. And we also always need to bring it back to the usage metric, which drives the failure characteristics of your system. So a reliability growth plan, or reliability growth testing reliability growth testing is always based on a reliability growth plan like this. And there's lots of problems with this curve because although we have the Dwayne failure pattern, we don't know where we start. We don't know how many failure mechanisms our device has, and we're not entirely sure what that pathway is going to look like. So, for example, if this military vehicle had one massive failure mechanism, that is, this failure mechanism was the only failure mechanism this military vehicle had, and it caused our vehicle to fail once every 1,000 kilometers. Well, all we need to do is observe that single failure mechanism, come up with a corrective action, and we've virtually eliminated all the dominant failures of that vehicle. But let's just say this military vehicle has thousands of failure mechanisms. Let's just say that the top 20 of those failure mechanisms are the dominant failure mechanisms. So even though this military vehicle, which has thousands of failure mechanisms, which could still have the same reliability characteristics of that other vehicle I told you about with one, is going to take a lot longer to grow its reliability because there's so many different elements of what makes it weak. And so this idealized growth curve is problematic because it's based on assumptions. And beyond that, this curve essentially measures the competence of your design team. So if your design team is really good at coming up with corrective actions, then this red curve is going to increase. Or if there's a constrained budget, because we only do reliability growth testing at the end of our production process, and therefore our design team is really limited in terms of what they can actually do, so they'll come up with less effective corrective actions, and this idealized reliability growth curve won't increase as quickly. So from a planning perspective, there are so many assumptions about where we start, how fast we grow, where we go to, how many underlying failure mechanisms there are, how competent our team is, et cetera, and the ability for our team to incorporate corrective actions through competence/funding. That really is not it is a problematic framework where a lot of people think this is exactly how reliability will grow. That doesn't mean it's not useful, because this now gives us a plan. It helps us work out if we are on track once we start getting a little bit of data, but it also helps us work out if we can perhaps terminate testing early. But it still comes with all those problems we talked about, where we have to base it on assumptions, and we typically only do this towards the end of our production process, once we have a fully functional prototype that can be tested in at-use conditions. Now, the client I was working for, they wanted, quite rightly, to know how this reliability was going to grow with respect to time, calendar time. As we know, most vehicles accumulate damage and usage that is measured in terms of distance. That is, if you expect a vehicle to drives 100 kilometers to have a certain number of failures, you'd also expect that same vehicle to have twice as many failures when it drives 200 kilometers. You can't say the same about time. That is, you can't expect a vehicle to have exactly twice as many failures if you observe those failures over 2 weeks versus 1 week. Of course, if they're traveling the same amount of distance each day, you would, but that's not the point. The idea is that we know distance is a really good usage metric for things like vehicles. But this is what that same curve looks like when we transpose it onto calendar time. So reliability growth curves should always be brought back to calendar time to inform test scheduling. And all this comes down to is that there are different test usage rates. So by bringing those test usage rates back into accumulated test hours, we could come up with this really funky looking reliability curve based on the previous curve. And all we've done is simply replaced test duration in terms of distance with test duration in terms of calendar time. And yeah, this becomes quite useful, especially if you're able to work out if this does at least largely represent your team's progress. So let's go back to our little road in Norway, the very start of this conversation, where design for reliability is all about finding the most efficient path to reliability as quickly as possible. If you do reliability growth testing and that's your main way of making reliability happen, you are almost certainly not going to find the most efficient and fastest route to where you want to go. Karen asked, what is the impact of wear out modes? It's a broad question. I might ask you to expand that question a bit or clarify just a little bit so I can understand what you're what you're moving towards in terms of those wear out modes, those failure modes, which are based on the accumulation of damage. While Karen is typing away, I'm just going to reintroduce this slide here, or this image here, which represents effort without outcomes, where we do lots of stuff, but don't know what those vital few things are, or we do what the standards tell us, or we do what worked last year, and not what the terrain of our device is asking us to do. So reliability growth is all about actually going from point A to point B. But reliability growth planning simply comes up with a length of road. It tells you how long testing should be based on your design team removing corrective actions efficiently, based on the test uncovering those failure modes, based on your prototypes being representative, et cetera, et cetera. So a lot of people think reliability growth planning is simply all about coming up with the length of road, but that doesn't replace design for reliability. So Karen asks, if our use failure modes are fatigue in 4 to 6 years and test duration is for vehicle growth only, is only 2, this seems like another limitation. Completely understand your point now, Karen, and that is a fantastic observation. Reliability growth testing, as a rule, doesn't cover the full service life of your system. So this military vehicle, for example, is supposed to have a 20 to 40 year service life. There's no way known reliability growth testing in at-use conditions can uncover those wear-out failure modes that are going to drive when you need to retire your fleet. So you will only understand, at the very least, the very early part of your service life, which is another limitation for reliability growth. John asked, doesn't reliability growth assume each prototype is new when it goes into test? What about upfitting existing fleets with new components or software, i.e. new transmission tested in an old truck? It's a very good question, John. And yes, there are some models out there which allow the reliability of your prototypes to improve, at least in the plan, based on, again, some underlying assumptions. So there are some models out there which allow you to do that. But the main point of reliability growth is to model the improvement in the underarching design itself. So there are, like I said, there are some other, there's some models out there which can do exactly what you're talking about. But again, there need to be some assumptions made as well. Brian states that depending on the usage patterns, you can possibly eliminate null time, plus have to consider acceleration factors of test conditions versus actual. Completely concur, Brian. However, in the industry, for whatever reason, that is seen as sacrilegious, or at the very least, disqualifies that test being designated as a reliability growth test, even though I like where you're heading. Kevin suggests that this only covers infant failure modes. And yes, that is true to an extent. Of course, when you're talking about military vehicles being driven over cross-country roads and dirt tracks, things will fail fairly routinely. And that of itself is not a huge, you need to expect at least some of that. But yes, you will only cover the failure modes, you will cover as a general rule, more infant mortality or wear in failure modes, or those issues you have at the start of your design process, start of your service life, as opposed to the end. But even better, even more than that, Kevin, many of our infant mortality failure modes and wear in failure modes are based on manufacturing, full rate manufacturing. Reliability growth tends to be conducted before that. Adiola says that I have seen reliability growth tests, I'm guessing, show that part replacement should occur at specific intervals to keep the reliability stable over that time. So preventive maintenance a part before it wears out to bring up the reliability of the system. That is an interesting topic, because you should be servicing your vehicles in reliability growth tests, because these are supposed to be at use conditions. So if you're going to service your vehicle every 5,000 kilometers, for example, in the real world, then you have to service your prototypes every 5,000 kilometers in reliability growth testing. And so that is not necessarily to keep reliability stable, because the ultimate aim of reliability growth testing is to, very controlled and statistically, let's just say formulaic way, track how reliability improves over time. That's the main point of reliability growth testing. So there's no real benefit in keeping reliability stable from a preventive maintenance perspective. You should be conducting servicing on your prototypes as you would in the real world. So reliability growth planning, as we've just looked at, those two charts I've showed you, all they do is they just tell you how long, well, what reliability growth improvements you can expect after you make a ton of assumptions should you implement a corrective action for every single failure you come across. So it's all about how long that road should be and not the underlying principles, not the direction that makes those improvements happen. So let's go back to our continuum of testing. On the left-hand side, we have improve reliability. On the right-hand side, we have measure reliability. And reliability growth, I always indicate as a measure reliability test, even though reliability growth testing, by its name, suggests we're improving reliability. The answer to that is yes, we are improving reliability from a very textbook perspective, but because we're using very mature prototypes, because we're using because we're conducting tests in at-use conditions and not accelerating, we often have limited capacity to make really cool corrective actions as early as possible or as feasibly as possible, to the extent that we sometimes have to, when it comes to reliability growth testing, incorporate corrective actions that are band-aid solutions. I've seen that happen too many times for this to be considered an improved reliability test. What we want to do is grow reliability the way we showed with our smart lock, where before we start doing detailed design, we use our wonderful corporate knowledge to understand the likely weak points of our system and design them out of our system to make sure our first design is a reliable design. That's reliability growth. There's no two ways about that. But reliability growth testing is so constrained that realistically it quickly devolves into a measure reliability test. On the right-hand side, I said we come back to this later on, we have demonstration testing. Demonstration testing I don't enjoy, because it requires, again, that we test our things in actual use conditions. It's not accelerated, it's very, very slow. So it's very, very similar to reliability growth testing, except that in demonstration testing, we are not allowed to improve design. Again, there is nothing written about that, but it's just the way it works in the reliability industry. And a typical example of a demonstration test is a PRAT, a production reliability acceptance test. So that's, in a nutshell, is reliability growth testing. It's all about using Dwayne's failure pattern to come up with an approach to testing which allows organizations to track or get some level of statistical confidence that the MTBF is improving or the failure rate is decreasing as we go through testing. But the problems with this is that reliability growth testing is so onerous as a result, because it takes so long and it's so slow that it tends to suck away all the oxygen from your production team that could be used to actually make reliability happen in your first design. And so I've seen many organizations simply look at reliability growth testing as the tool to make reliability happen. But again, by the time you produce this final prototype, the scope to do sweeping corrective actions cheaply and effectively is somewhat limited. Now, there is nothing wrong with reliability growth testing if it's part of a continuum of a genuine strategy for reliability. But it should always be the final thing you do after you have made your first design a reliable design through Vermeers or Holt or whatever design for reliability tool works for your system. Reliability growth testing is not designing for reliability. It's simply finding out what those weak points are. Design for reliability comes next. And again, if you delay it in your production life cycle, then it becomes harder and harder to incorporate. So let's go back to, why do we need to test to get data and create information? It comes back to decision making. Decisions are made every step of the way. So this poor old young engineer who's going to be designing the hydraulic pump of a military vehicle, for example, is going to be asking questions like this as he goes through his daily pattern. Is my thing reliable enough? What is reliable enough? What's going to break? What do I need to do next? Now, in many of my webinars and courses, I talk about the 3 enemies of reliability, and you're going to see them again if people who have seen me talk in the past. The first guy is our ponderous professor. He is one of these guys who loves reliability growth testing because he wants data to analyze. He wants to measure, do lots of tests that measure stuff so he can analyze data. He is not here to help. Then we have our process zealot who's just simply interested in compliance. And many customers simply say, oh, use Mill Handbook 189 Charlie to do reliability growth, and off you go. And that is simply a standard or an approach that's written for everybody else's ideas and systems and not yours. Or it could be embedded in a contract. It of itself is not growing reliability. And this is sometimes why we see reliability growth as being selected or down selected as the penultimate tool for making reliability happen, when in practice, it replaces design for reliability. Then we have this guy over here, the infant manager, who's always saying, do it faster, do it cheaper, and make sure it passes. Now, if this guy knows that he's doing reliability growth testing later on, he essentially pressures everyone to not waste their time making it reliable now, because that's going to happen in the future with this reliability growth test plan. And so that's one of the many issues that reliability growth testing comes up with, introduces. And I've seen reliability growth test plans that take years, and that just, it can't help but suck away any motivation to do reliability early in many organizations. So when it comes to growing reliability, always ask yourself, are you trying to improve or measure reliability? These are very different tests that result from the answer to this question. Either way, you still need to know the vital few. And remember that reliability is a measure of your system, and confidence is a measure of you. The best form of confidence you get is when that confidence you generate through repeatedly tackling those corrective actions, those vital few, through your familiars, your halts, your fault tree analyses, all those activities that you execute well at the start of your design process to try and prevent as many failures from happening as possible. Because when you do that, you generate confidence through understanding. Confidence through statistics is a lot harder, it's a lot more expensive in some cases, or most cases, I should say, will never approach that confidence you get from making it right the first time. So, are there any questions on reliability growth testing? Do we all appreciate the fact I didn't include a single equation? Because it seems like every other week, a new reliability growth model is produced, which has a slightly different equation. Any questions, any comments? Adiola asks, thank you, will slides be available? My apologies, I usually provide a workbook with my webinars, as is the case. As what happened earlier today and late last night is my Microsoft Word document, which I use to generate said guidebook. There is something corrupt in there. I can't work out what page it's on, but I need to keep going through and working out where that bit of corruption is, and effectively prevented me from creating a PDF guidebook. I'll try and get that to you guys as soon as possible. Thank you for your feedback, Sebastian. Hopefully it's going to help you moving forward. Of course, if you do need to do reliability growth testing, then there are plenty of guidebooks out there with the equations I didn't dare touch today, which I have personally used as well. And of course, if you also need to have any questions, I should say, feel free to reach out. Excuse me. Thank you for your feedback, Karen. Yes, the recording will be on Ascendo Reliability, as all webinar episodes are. So that will be there for perpetuity. Thank you, Adiola. Much appreciated. Kevin asks, how many companies are you seeing actually using this approach effectively? And the answer is not many. Reliability growth testing is used almost exclusively in where you have a military or a government customer. Reliability growth happens all the time. That's where we improve reliability from designing out all the weak points of our system. So reliability growth is the outcome, or what design for reliability is all about. Reliability growth testing, however, seems very military centric. And I think that's because there are so many problems with the approach of creating such a huge focus on reliability growth testing, which usually happens just before manufacture when it's very late in the production process. Many commercial organizations don't see the value in it. Thank you, Van. Much appreciated. Adiola says that reliability growth testing occurs at our semiconductor company, albeit I think it could get more attention and time. Now, that's a good point, and I should probably correct some of my sentiment earlier, especially for electronic components, because electronic components are different to military vehicles, developmental military vehicles. You can have lots of components tested relatively inexpensively, and you don't reinvent the capacitor each and every single year. So reliability growth testing can be used, but I dare say, Adiola, that's not the only design or only approach to making reliable components that your organization uses. I think it sounds like it's part of your continuum. Brian says, we do reliability growth testing of our products, very large machines and often single samples. And I should also correct myself again, perhaps. I don't know what your industry is, but in asset management, I should say, we often do see us try to grow reliability of big pumps and big hydraulic machines and big valves as we try to improve the efficiency of our plant. So we will effectively do reliability growth testing for our big machines, which we own for a long time. And that's the key. We own it for a long time. And so therefore we can invest lots of time and effort into trying to improve its reliability over time. But I don't know exactly what your background is, Brian, but there are a couple of examples. Adiola confirms that, yes, reliability growth testing is one of the things that you guys do. Fantastic. Not a problem. Mining machines, there you go. So it's not, you wouldn't call mining machines asset management, or some do, I should say, but we're talking about big machines that you're going to try and continually focus on, improve, and apart from that, do equipment husbandry to cajole it to improve its reliability over time. In effect, you're doing, I'm guessing, reliability growth testing as part of your operations. Is that right, or have I missed the point? Just waiting for Brian to type in a response. Do an initial period. Okay, no worries. I have worked on quite a few mining sites where they do have what could be described as reliability growth as part of their ongoing approach to managing their equipment. But at the end of the day, I've seen different approaches work really, really well. There's no right way, but there's plenty of wrong ways. No worries. Thank you, Jason. Much appreciated. Any more questions? Any more comments? Thank you, Long Chun. No, I was a bit down on reliability growth testing, and I think my pessimism on it as an activity should be taken, is very real. It only works when it's part of a bigger strategy that is mature and works. At some point, you are limited by the customer's maintenance department. Yes. Yes, I have worked with probably your customer's maintenance department in the past, it would appear, Brian, but again, you can't enact huge corrective actions to the design, at least during operation. You can do wonderful things, I should say, with optimizing maintenance and maintenance regimes. And that is a corrective action. A corrective action is working out how to change your maintenance strategy. There's nothing wrong with that. Thank you very much, Kevin. All right, any more questions before we call it quits for the day? No worries, Fred. I think we're good. And of course, if any other question comes up after this conversation, feel free to reach out. Thank you, Karen.